I meant it because some people made a mistake on it, so I just want to be sure everybody's fine with it, right? So should I do it or everybody know it?
I think since we went over it, I mean, it should be fine unless anyone has any objections.
That's what I'm saying. If anybody has an objection on this, I can just do it. Okay. Anybody would like me to do this? If yes, write in the chat yes. If no, just write no.
I do have a question, Professor.
Yes, sir.
Okay, so how come we always use the last two terms as the top variables?
Okay, here. I think it's better to make it. Look. 1, 2, 1, 2, 3. Everybody remember from the recorded lecture that we said left to the right, it's called like this. So gonna be A, B, C, D. Otherwise, you're gonna go in something that's called orthogonal K-map. I think I mentioned this before. Everybody agree?
Yes.
Sure. So gonna be 0, 0, 0, 0, 0, 1, 1. Scheiße. 1, 1, 1, 0. So here is gonna be 1, 0, 1, 1, 1, 0, right? And then here gonna be 0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 15, 14, right? So gonna be 0, 1, 2, 3, 10, 11, 10, 11, right? 12, 13, 14, 15, and 8 and 9. I'm right? This is a group, and this is another group. So end of the day, f as a function of a and b and c and d is equivalent to, in the first group it's gonna be a, or the second group is gonna be b complement. There is no more than that. There is nothing else can be done. Is it clear to everybody?
Yep.
It's one shot answer. Now let's go to this one. This is my lovely part, because you know it's very easy, right? If you take this and this one, and this one, z is bye-bye. Everybody agree?
Yes.
So I can write it like this: x, y complement, and x, y complement. And then you know here and 1 with z. 1. And then this is x. Somebody's coming. I'm sorry. Then this is gonna be x, y with x, y complement, right? Then this one, Captain De Morgan. Everybody agree? So if I do like this, is equivalent to what? X, y complement, x, y complement, which is x, y complement. So this is what? Everybody understand what I did?
Yes.
The rest of the nation?
Yes.
Super. Now we'll move forward. This is very easy, right?
See.
So let's see what it's gonna be. So you know, A ORed with B, A ORed with B complemented, right? Then they're gonna be A with A, B complemented. Then you know here it's gonna be A with A, B complemented, right? Then it's gonna go here to be what? OR together, right? That's it. And then you know you're gonna go in one more all time. But you know, I think while you're doing this, you can actually what? You can optimize, right? Everybody understand what I'm doing, right? So for instance, you know, here I can optimize this, right? Why I can optimize it? Okay, so I can optimize it. It's gonna be A ORed with A complement, B complement. I'm right?
Yes.
Yes.
Then, you know, I can take it here to be not gated. So I do like this. It's gonna be what? It's gonna be A complement, and it was A with B, right? So in that case, it's gonna be A complement
Yes.
B, right? So this one is gonna be A complement B, right? And this one is
Sir.
yes,
Oh, no, I was agreeing.
it's good, right?
Yes.
Okay. Here it's gonna be what? Here it's gonna be A complement B complement, like this, right? Then you order them together. So gonna be what? It's gonna be A complement B with A complement B complement. I'm right? Which is A complement. Oh, Jennifer again. Okay. So that's basically that's gonna end up being here A complement, right? And then you take it with this one. It's gonna be A complement. Is this correct?
Shouldn't it be a complement of A and B?
We can see. We can
Surrounded.
see what we can do. Yeah, we can actually clean it up more, and we do it fast. Maybe I lost something in the middle, so it's not really hard to do it, right?
I think it was.
I think I lost something in the middle, which is you're right, because you know here is gonna be A or B. Here is gonna be A or B complement, right?
Yes. Yes.
Then this will go here, right? So that's gonna be what? It's gonna be A B complement with A, right?
Yes.
Then here we're gonna be A with B complement with A and complement.
Yes.
Then this gentleman gonna be the same together. So you know, let's do this one. Let's call this X, right? So X is equal what? A B complement, right? Ordered with this guy, right?
Yes.
A B complement, A complement, right?
Yes.
So let's finish this branch. So you know, do this trick. So gonna be A B complement with they're gonna be what? They're gonna be A complement, B complement, right?
You could also do the absorption law since you have a not A or B or not
you
A or
can,
B.
yeah, you can do the absorption law. Yes,
Yeah.
you're right. You're right. That's correct. So in this case, this will be what? One.
Not A or B or A.
Not A.
Oh no no. Like the big bar. Not
Not
A or B. So that one.
A or B. That's basically what you're thinking about. Everybody understand what he said, right?
And in the middle, it's an or, a plus.
You mean here or? Okay.
Yeah. And then or on the outside with an A.
You mean here, right?
Yeah. Because so basically, I did absorption law on the first two terms.
That's actually one of the rules. Yes. Okay.
Yeah.
Then you know what else you're gonna do after that?
So after that, what you could do is De Morgan on A or B not.
Oh, I know what is the problem because I forgot. I made it. I considered this or. That's why.
Yeah.
You know, you're right. It's gonna be AB. Yes. You're right. Even if I follow with my rules, it's gonna be the same thing. You're right. I can just move forward here and continue. You know.
Mm-hmm.
So it's gonna be here equal to the A B complement with A B complement, right? And it was A complement, right? That's correct. So you know you can say A B complement, or, and then they're gonna be A B, and it was A complement, correct?
Mm-hmm.
And then they're gonna be A B complement, and they're gonna be B A complement.
Yes.
That's correct?
Yes.
Okay, so that's actually this term. With this term is this one, right?
Yes.
and they are ANDed together. So that means, you know, end of the day, gonna be what? It's gonna be A, B complement with the B, A complement ANDed with what? With this one, right? With A, B complement, and here is A, and everything is complemented. That makes sense? Juan?
Yes.
In that case, you know, you can just like, you know, everybody. So end of the day, gonna be what? It's gonna be A, B complement with the B, A complement time. We need to break this up, right? So gonna be A, B times what? Time A complement. So they're gonna be A, B complement, B, A complement, and it was this A gonna be B, A complement. Is this correct?
Yeah, and then from there you can use a rule and just say B or B and A complement.
Yeah. So this one is gonna be the same, right?
Yeah.
It's gonna be B, A complement, and then you know you will break up this, right? So they're gonna be A complement, B complement, right?
You could also use distributive law and keep it together.
You can do that. That's correct. Or you can just go ahead and just say, you know, A complement, B complement times B A complement, right?
Yep.
So end of the day, because this happened and this happened, then you know this is gone. So we just have this.
Yes, sir.
Make sense? Is it clear, everybody?
Yes.
Super. Now this one should be T complement. How many of you made the T complement? One?
I did.
Yes.
Did it work with you, T complement?
Yeah.
Yeah.
Okay, so everybody's fine with it. Or should I do it?
I'm fine with it. It was easy.
It's very easy, right? I mean, you can think about it like this, you know, here is an OR, right? So this area gonna be RST complement, right? Then here gonna be RS complement. They're gonna be ended here to be RS complements with T, right? Then this was this B, and then you complement. It's like, you know, the same thing. So it was fun. So basically everybody's fine. Unless somebody has a problem with. Who has a problem with this question? Should I do it, or, you know, should I move forward? Hello?
I'm good.
Yeah, let's move forward, Professor.
Okay, let's move forward. We do one more time. Here, you know, design and implement a combination circuit that converts XS3 to BCD. It's very easy. Why? We have like this. X3, X2, X1, X0. Then it's gonna be here B3, B2, B1, B0, right? Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'm right? Then, you know, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Then there are going to be 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Then 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That's perfectly fine, right? It is axis 3 to BCD. Axis 3 is from 3 to 12. That's from the number system, chapter 1, right? So there is no 0, there is no 1, there is no 2 in axis 3, right? So there is no equivalence. So that means I can just make it like this. Make sense? Do you guys agree? Hello?
Yeah, it makes sense.
3
Yep.
is gonna be 0. What is this? 3 is gonna be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Huh? Is there any 10? This does not exist. After 12, we don't have. 13, 14, 15 is not exist. So this area is bunch of x's. Does not exist. That makes sense? Then, you just make a K-map and you'll be done. So it's a very good practice of using K-map with don't care. That's basically what it's actually we need to do. That's it, right? So you need to make how many K-map we need?
4.
4 K-map. And I know exactly what is my NaN gate equivalency in every single gate, so I can just use it. So that's a very good practice for the K-map with don't care, and on top of this, the equivalency, gate equivalency using NaN gate as I did before in the number systems, and you can return it to the first 3 recorded lectures in this course. That makes sense? Or should I do it?
Well, if you want to. I'd like to see it, honestly, because
if somebody like to see it, how many of you in favor to see it? Should I do it? Okay.
Yeah, Professor, I'd also like to see it done.
Yeah. 1, 2, 3. 1, 2, 3. Left to right, right? E3, E2, E1, E0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0. 1, 0, 1, 1, 1, like this. 1, 0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 15, 14. Okay, I'm actually targeting B3, so I'm looking for B3 as a function of the E3 and E2 and E1 and E0. Do you guys agree? Okay, now I'm looking for this, right? Up to 2, everything is x. So 2 is x. So 0 is x, 1 is x, 2 is x. Right? And then 3, whatever. So we just have how many? 11 and 12 are 1, right? 11 and 12 are 1. And then, after 12 is what? 13, 14, 15x, right? 13, 14, 15 are x. Sounds make sense? Does this make sense? Juan?
Yeah, very much so.
Okay, so now we're going to be 0, 0, 0, 0, 0, 0. How many group do we have? Somebody, 2. Yes, correct. 1, 2. So in that case, the first one is going to be E3, E2. ORed. The second one is going to be E1, E0 with E3. We got B3, right? What exactly I need now? I need to convert this into a bunch of NAND gates. That's not really hard for me, right? Because this is AND, so I need to know what is equivalency of AND using NAND gate, and I need equivalency of OR using NAND gate. That makes sense?
Professor, can I take a take a look on the truth table? Yeah, right here.
Yes, please.
That's it. Thank you.
Okay. Should I make the other one? I will just make one more. Okay. 1, 2.
All right, thank you.
You're welcome. 2. Here. Which one you guys like me to do? I made B3. Which one? Somebody pick.
B0.
B0. E3, E2, E1, E0. 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 1, 1, 1, 0. Then 0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 15, 14. Then, you know, somebody said 0, right? So 0, 1, and 2 are x, right? 0, 1, and 2 are x. Then what happened after that? 4 are 1. Where's 4? 4 is 1. Then, you know, after 4 is 1. 6 is 1, right? 6 is 1. 6 is 1. 8 is 1. 8 is 1. 8 is 1. Okay, we're done here. Then, you know, 10 is 1. 10 is 1. Where's 10? Okay, 10 is 1. Then 12 is 1. Where's 12? Is 1, right? Then 13, 14, 15, 1, right? X. 13, 14, 15, X. Sounds good? How many group do you have? Just one group. Make sense? We done. Do you guys agree?
Mm-hmm.
In that case, I can say B0 is equivalent to E0 complement. Right?
Yeah.
Make sense? Okay, and move forward and you'll be done. So straightforward, right? And this one also is very straightforward, right? If you have a multiplexer, how can you build X1 multiplexer? You can build two X1 multiplexers, use an OR gate, like grouping it. That can make that makes sense, right?
Yeah.
Yeah.
And you know how to do it, right? Or should I do it?
I think I messed up at the end of mine, so it might be good if you did it. But...
Sure. I mean, if I can make a table like this, huh? Yes, sir.
7.
If I say
Yeah, I don't think he's talking.
S2, S1, S0, right? And I say output, for instance. I can just 1, 2, 3, 4, 5, 6, 7, 8. That's one way. So 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4, right? When it's 0, it's going to be I0, I1, I2, I3, I4, I5, I6, I7, right? So I can write an operation in a function of those guys with those guys as well here is equivalent to S2 complement, S1 complement, S0 complement with I0, OR, and you move forward, right? S2 complement, S1 complement, S0 with I1. Then S2 complement, S1 S0 complement with I2. Or da da da. I mean, this is a difficult one, right? Easy way, you just make a multiplexer 2x1 and, you know, just like, you know, you make the propagated tree. That makes sense? Who was asking me actually? Joe or?
I did. So I had, when I built it, I had for the switches, for the I had two lines for each switch, which was one was just a line that would go straight into it, and then the other one was a line, and I used a NOR gate to make a knot, and then I attached those accordingly.
I mean, you can do this, right? Have you noticed this? You just need OR and OR and OR and OR. You're gonna have every line like S0 and the invert of it, S1 and invert of it, S2 and invert of it, right? I mean, implementation wise, it's like this, right? You can make it like this. You agree?
Yeah, I'm just confused because you said you said I had the majority of it, but I'm still missing some parts. So I was just curious as to what that is.
You did like that?
Or actually, no, I had 3 switches.
I mean, yeah, it's what? S2 what? Let me see. S2, S1 is 0, right?
Yeah.
Then you will go, this is NOR gate, this is NOR gate, this is NOR gate, right? Then you're gonna take them to AND, right? You have to AND them.
Right.
And then you make OR and OR and OR and propagate of it. Did you make that?
Yeah, then I have all of those depending on then each of them has a bit going into it, which is knotted. And then those are also going in, each bit is going into a NOR with the corresponding switches.
I can double check your answer 1 second.
Okay.
2300, right? And it's midterm 2, right?
Midterm 1.
There is no midterm. Pure. Great. What? Oh, I'm looking for 5300. Yeah, sorry. It's a good sign. Now you are in 3300. Yeah. Okay, sir. Oh, your grade is really cool, actually. Come on, dude. Anyway, so what was the question? Question what?
It's number 4.
4. Let me see what you're doing. Who's B0? B0. Okay, how can you build NAND gates using OR gates?
Well, using NOR gates?
Mm.
Yeah, well, according to De Morgan's, if everything, if you're NORing everything, and everything is the opposite of what it should be. So if it's B0 and then switch 1 should be switch 1 not, switch 0 not, switch 2 not, everything should just be knotted. And then when you're NORing everything, according to De Morgan's, it should go back, and then everything should be ANDed together, opposite to what it is. So like if you look at the first one, I have like B0 not plus S0 not plus or plus S0 plus S1 plus S2, and then in parentheses it's all knotted. So then, right, according to Morgan's, wouldn't it be all of that?
Wait. Because you already have a bunch of wires coming from the NOR to NOR and then NOR to NOR. I think that's the problem. So let me see what it is.
Yeah,
so,
I wrote the output of each one.
No. I mean, let's say I would like to build an AND gate using NOR gate. How are you gonna do it?
Right. I mean, I thought, I don't know. Does my math not check out if you were to?
I mean, wait. Let's do it. It's not a problem.
Okay.
F is equal A B. That's basically our target, right?
Sure.
And NOR gate is A B like this, right?
Yeah.
So pretty much this has to be like this.
Right. Oh, right. A or B.
So I want kind of like this.
Mm-hmm.
What is this? Anyway, be complement like this, right? And then if I take it to the if I take it like this, right? What will happen? It's gonna be A complement, B complement like this, right?
Right.
Right?
Yeah, that's what I did.
Nope.
I'm not...
Look, you didn't. Those are missing, right? You already made it wire. Some of them are already cleared up. How did you clear them up? See, B, for instance, B0, you already have one not gated, right? But the rest are not.
Oh, well, they're connected to, like, some of the switches. I have 2 lines for each switch. One of the lines for the switches is knotted, which when it goes through the NOR gate, it would then be, actually that's like the one. And then so I have 2 lines for each which one.
Well, you're saying that, you know, the original not gate, it will be taken, this not gate, then it's gonna go away, right?
Yeah.
But that's what I don't see in front of me, you know. Look here, you know, you have this is 0. Because you already made this no, right? You should put the norm and then, you know, just like grab it up there, you know. That's actually what was confused me.
Oh.
You understand what I'm saying?
So if I would have just written like S0, like if I instead of doing like
like, you know, now you're gonna take whatever to whatever to whatever to whatever to whatever using this, right?
Yeah.
Then, you know, there, you know, you can group like this. I think that's a group. But, you know, here it's show that, you know, you have S0 complement. You know, that's why it's make it like, you know, weird to me. But, you know, that's perfectly fine to me. Okay, you get the 4 points.
Oh, sweet.
So, you know, that's not problem. So why you didn't go to my office hour?
I was just gonna ask you in class because I figured it was just like
Oh, just pick up my office hour. That's it, you know.
All right.
What's your name, sir? Yeah, your name, sir.
Me?
Yes.
Griffin.
Griffin. A, B, C, D. I'm in 20th, right? So I'm looking for Griffin. Your name is Griffin, right? So I'm looking for.
Yeah, Griffin Curland.
Curland, yes, I'm looking for Curland. So Curland is something in the middle. I'm not finding your name. Oh. Next time, if you have a question, you know, please don't hesitate. Just go to my office hour. You know?
Okay.
So you have given, and this is actually the midterm, right?
Mm-hmm.
So I said you're gonna get the 4, right?
Yeah.
So, you know, perfect. Okay. So is it clear to everybody what I did, right?
Yes.
Okay. Now we're gonna move into the last question. Last question is new for everybody, but it's not new for everybody. That makes sense? What does it mean? We have the rules, right? What was the rule? 2-bit comparator. So we just have something like this. This is in 2-bit, and this is in 2-bit, right?
Wait, Professor, is it a 2-bit comparator or a 2-bit multiplier?
I'm telling you. Normally, you know, this is 2-bit multiplier, right? But, you know, what I give it to you in the lecture is comparator, right? But I didn't tell you that, you know, I didn't tell you to multiply. It doesn't mean that, you know, everything it has to become, you know, this is the design course. So I'm giving you an idea about how can you design a circuit, but, you know, question can come into any circuit. That makes sense? But concept is the same. So, you know, if I design 2-bit multiplier, how I'm gonna do this? Really easy. I'm gonna do it in front of you from scratch. Think with me. Now this is multiplication, and this is A and B, right? What is the output size will be? I don't know. Let's say that, you know, Professor Ali didn't tell us. You don't know. I don't know. Let's call it P. What is the maximum of A can be? If it's 2-bit.
1.
3.
Oh yeah.
If it's this 3 and this 3, and I'm multiplying them together, what is the output will be? 3 times 3 is what? 9. 9. 9 is representing in how many bits? 4. Right? So out of this multiplication, A multiplication B, size-wise of C as an output. So the size of A plus size of B is equivalent size of C. That's general rule multiplication. Who made this rule? I just made it in front of you, right? How? A is 2-bit. So what maximum number can A can represent? 3. B is 2-bit. What maximum number B can represent? 3. 3 times 3 is what? 9. 9 represented in what? 4. Because it's 2 plus 2 is 4. That makes sense? Then we're gonna make exactly the same table, right? So we're gonna have come here and say that this is B and this is A. B1, B0, A1, A0. And then, you know, we have 4 bits. Oh, so it's gonna be what? B3, B2, B1, B0. How many states do we have in this table? 16. It's gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? Keep multiplying. 0 times 0, what is the output? 0. 1 times 0, 0. Pretty much everything here is going to be 0 up to here. It's going to be 0. This is ridiculous. Here. Now, 1 times 0 is still 0. 1 times 1 is 1. 2 times 1, 2. 3 times 1, 3. 0 times whatever, 0. 1 times 2, 2. 2 times 2, 4. 3 times 2, 6. 0 times 3, 0. 1 times 2, 3. 3. 2 times 3 is what? 6. 3 times 3, 9. That makes sense? Hello?
Mm-hmm.
Is it clear to everybody? Right?
Yeah.
So in that case, I'm gonna use how many multiplexers? I can just make it exactly as I did before with the comparator, right? I can use 4 multiplexers, right? That sounds make sense?
Yep.
And we'll make this tricky thing. How big this multiplexer can be, whatever. Can make it what's called 16:1 multiplex. Since I didn't say exactly what is the size of the multiplex, did I say it? Oh, I didn't say. That makes sense? Should I continue? In the solution is why I keep adding weird stuff? Why I keep adding? I'm here, right? I need this page. So I'm looking for B3, for instance. You know, worst case scenario, I can just come and say, here's a multiplexer. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. What is this going to be? B1, B0, A1, A0. 0 to 15. And what is the output? B3. What is here? I can just say my source is A is equal 1. I'm just making that story, right? Then any of this, and all of them will go to 1, right? Look at this trick, right? And then let's say 0, right? B3 is 0, right? So basically I can just make NAND gate like this, and I put here the 1. And move forward. Does make sense?
All right, I see it. I see it.
See?
I overcomplicated it a little bit.
It's easy, right?
Yeah.
I mean, because I didn't give you even, what is the size of the multiplexer, right? Why you make it complicated on yourself? Just like big one and that's it.
Yeah, because what I was doing was, I think I know what I went wrong with. I think I was
Full adder.
yeah, I was decomposing the half adders into.
I know. I mean, that's actually, you know, what we have. Wait, I didn't tell you the offer I'm gonna give you guys. You know, at least you know we are learning here. What is the offer I'm offering you? Imagine. This is
We get half credit back.
This is a brand new course for you guys, right? You never seen digital logic before. Do you agree?
Yes.
Yep.
Here is the offer. Quiz number 2. If your grade is higher than quiz number 1, I will match your higher grade. What does it mean? What does it mean? Let's say that quiz number 1, I got 20 out of 100. Quiz number 2, I got 100. Then you will get 100 in both of them.
Oh, nice.
But wait, let's say you get in the first one 100, but you got in the second one 80. I will add both. So the privilege, if you get better. And the same thing for midterm. Sounds fair.
Professor, what did you say about same thing about the midterm? So if we get a better score on the second midterm,
1 and midterm 2. You know, don't forget we have two categories, right? We have quiz and midterm, right? Midterm 1, your grade is not that great, for instance, right? And you know, you studied hard and you looked to the record videos and everything. And then when you went to the second midterm, you got 87. But you know, your grade in the midterm 1, it was 50. So your final grade for a category called midterm, it will be 87. It will be the highest.
that's good. Thank you.
Very fair.
Thank you.
But if you in the first one got 80 and in the second got 60, I'm gonna take 80 and 60 and add them together.
That's fair.
Sounds fair for everybody?
Yeah.
No, I would like to see the rest of the nation. You know, you guys said yes, but I don't know what about the rest of the people.
Yeah, sounds good, Professor.
Okay, so that's basically what I want to tell you. Don't worry. We are here to learn. We are not here to fight or punish. We still have some time. So maybe I can.
We have one more question, by the way.
Oh, there's one more
'Cause you-
question. You're right. You know,
Yeah.
oh gosh, I forgot.
You said that was the last one.
That's an easy peasy lemon squeezy thing, right? Come on, I did it before, right? So you know, here, right? It was like this. And this one, you convert it to be NAND in NAND. That makes sense?
Is that it?
You're gonna make the bit full, you're gonna make the truth table and so on. It's in one we recorded the lecture before. Go ahead. Navan, do you have a question?
Yeah, is that the final answer?
Yeah, I mean, no, it's not. Come on, you know, it's not the final answer. Basically, you know, I'm just reminding you one bit full other look like this. But you know, look, all the steps. What is the all steps? That mean you're gonna make a table like this. Say that A, B, C, N, sum, carry out, right? 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 2, 3, 4, 1, 2, 3, 4. Right? Add 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 1. I'm right? Then I don't know what is this majority. So if I'm you, I would just go ahead and just say that, you know, majority. And I'm not sure what is this, right? And then I will look to those. Those are the input, right? Majority of 1. So basically here is 0. Here is still 0. Here is still 0. Here is 1. Here, because you know 1 and 2 zeros is still 0. Here, 2 of 1 and 1 is 0 is still winning, so it's gonna be winning. Winning 3 ones and there is no 0, gonna be 1. Then I will start compare. I will find this one is equivalent to this one. That makes sense? And then, you know, because I said NAND gate in the others, so you know this is going to be used in NAND gate. And this is basically what 2 XORs together. So you will remember how did you build the XOR before using NAND gate? You'll just do it and you'll be done. That makes sense?
Yeah, that makes sense.
What about you, Jamal? Make sense?
Yeah, that makes sense. That makes sense.
The rest of the nation, do you guys have any questions or concern regarding this answer?
Oh, could you scroll up a little bit? Thank you. Oh, Professor, I do have a question.
Huh.
So, the top one, the top output, which that'll be the sum, correct?
Oh, I'm sorry. The sum, yes.
Yeah. Okay. Okay. Thank you.
And the sum, you're gonna make NAND gate equivalent. While the majority is just like the block box coming from here. Sounds good? Okay. So
Yep.
that's actually aligned with chapter 4, right? The chapter we are actually learning, combinational circuits. That makes sense? Accessory gray code. Somebody can ask you to build gray code using multiplex. What are you gonna do? Same thing. I didn't give you decoder, right? Or did I give you the decoder?
No.
Okay, so now I'm gonna talk about decoder. So we are done with this, what's called? We are done with what? We are done with the midterm. Now we're gonna go into some part of the lecture and we'll continue next time, okay? So we're gonna learn a new element. It's called decoder. What does decoder mean? No, I don't think I went through the decoder. Do you guys remember? I did multiplexer, demultiplexer, right?
Yeah, you did those two.
I did the decoder, right?
Let me check my notes. I'll be right back.
Everybody know what is the decoder or not?
I could use a refresher.
Just like
Yes,
reverse
I agree.
operation of an encoder.
We don't have that much time, so you know we can just go in the decoder a little bit. So you know, decoder is basically, you know, you can come and say 2-4 decoder or 3-8 decoder or N2N decoder. That makes sense? Yeah. 2, 4, 3, 8, N2N decoder. That makes sense? So in that case, decoder can be done like this. I have an input and I have 2n of this input, 0 to 2n minus 1. What is this for? It's basically for labeling. So, you know, you are working in a post office and you would like to label stuff. And instead of calling me as Muhammad, you're saying 0045. Then, you know, that means as Muhammad. Then, you know, somebody would say, you know, 15-9, then it will be Juan. Then, you know, 9-18, it's Joseph. You know, 4-9, Luay. You know, 8-17, you know, Jamal, you know, and so on. You know what I mean? So it's making a way for, like, you know, how to say, decoding things. That means, you know, I'm taking something else to do it. And in the decoders, you cannot call everything at the same time. What does it mean? When is 0, 0, you know, the line based on the 0, 0 will be the one is activated. When it's, you know, 0, 1, that means the line with 0, 1 will be activated. Again, so, you know, let's have an example of 2, 4. Let's have an example of 2, 4. So 2, 4, that means, you know, I have here like this. Symbol wise is like a box like this. And you just write decoder. This is annoying, decoder. 2, 4. It means here is 2 bits. Let's call this S0 and S1. And then the output here is basically 0, 1, 2, 3. Let's call this D0, D1, D2, D3. Then the truth table will be basically controlling this black box will be the following. I have control S1 is 0, and I have D3, D2, D1, D0 as outputs. How many states this table is covering? 4. So it's going to be 1, 2, 3, 4. 0, 1, 0, 1, 0, 0, 1, 1, right? When 0, 0 happens, that means if you remember M0, M1, M2, M3, you remember this mean terms? So when a 0, 0 happen, what will happen? So D0 will be 1 and the rest will not be. When is, M1 happens, so gonna be like this. When M2 is happening, like that. When 3 is happening. So one input at a time will be what? Activated, the rest will not be activated based on the code you are calling as an input. So making circuit for this is not really hard, right? It's basically you're gonna have a bunch of ends, right?
It's really easy.
Yeah, it's too easy, exactly. So you're gonna do it like this. S1, S0, right? Then, we can have different colors. So, 0, 0, right? D0. 0, 1. Then 1, 0, right? Then if you continue like that, 1, 1, right?
Yeah.
So we build the circuit. If anybody asks you to build a circuit using equivalency of NAND gate, NOR gate, what are you gonna do? You just convert this to an or NAND, and you convert those by equivalency and so on. That makes sense?
Yes.
So if I want to build a bigger than this, let's say, 3, 8, right? Same philosophy, right? So, I have a box here and it has 3, 8, and you IC decoder. And here is 1, 2, 3, like this is 0, S1, S2, and here is what? 0, 1, 2, 3, 4, 5, 6, 7, right? D0, D1, D2, D3, D4, D5, D6, D7. Sounds good. Now we're gonna make the table again. So it's gonna be here what? It's gonna be S3, not S3 actually, I'm sorry, S2. S1 is 0, 1, 2, 3, 4, 5, 6, 7, 8. They're gonna be 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3. Then output wise is gonna be D7, D6, D5, D4, D3, D2, D1, D0. Gonna be what? 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. And 1, 2, 3, 4, 1, 0, 0. It's a diagonal, right? 0, 0, 1, 2, 3, 4, 5, 6, 7, 0. 1, 2, 3, 4, 5, 6, 7, 8. And then you're gonna do this coloring thing that I made here in the top, extending this. Second thing that we should learn about any combinational device, or we are learning, right? How can you build from a smaller one, bigger one, right? You guys agree? So imagine the following. The following is this, somebody is telling you, I bought an IC, and this IC is have bunch of the decoder 2.4, but I'm looking for expanding this to be 3.8. So how can you build 3.8 out of this 2.4? How can you do this? You have to learn about something that's called enable. Enable. Guess what is enable is? Somebody tell me, what is enable is?
So it depends if it's active high or active low enable. So if it's active high enable, if it's a 1, then the inputs are enabled, if that makes sense. If it's active low,
let me make it easy for everybody. So enable is the following. Imagine that your computer is connected to the electricity and you are doing your work, right? Because the electricity is going through the what's called the plug-in, right? Then your little brother was chasing you, and while you are doing the work, he just pull out the thing from the plug-in. What will happen?
Everything shuts off.
Then you will be mad. Exactly. That's enable. So if I have a block like this, like 2.4 decoder, and it has here S0, S1, 0, 1, 2, 3, like this. And I got an enable like this. When I do it like that, so I'm saying the enable here is active high. Why? Because this wire is connected. If it's equal 1, if it's equal 0, nothing will be working.
Oh, so it's like a power switch.
Exactly, it's a power switch. So in that case, I have 3 input in front of you, right? So I can come into a conclusion, say that, enable S1 is 0, right? If enable is 0, I don't care what is S0 and S1 because I have no idea what those guys will be. Or I would just put them in 0. That makes sense? When it will be important, when is equal 1? 1, 2, 3, 4. 0, 1, 0, 1, 0, 0. When this happen, 1, 0, 0, 0. When this happen, 0, 1, 0, 0. When this happen, 0, 0, 1, 0. When this happen, 0, 0, 0. So far, so good?
Professor, are we supposed to do 8 inputs?
No, why 8 inputs?
I mean, not 8 inputs.
This is 4 by itself.
Oh, I was thinking because we had 3, we had enable, select one.
Yeah, but this line is 4.
Gotcha.
Makes sense?
Makes much more sense.
So building the circuit is not that very hard, right? Guess what the circuit will be look like? Whatever we build up, everything will be ended with enable, right?
Yeah, that's what it looks like.
That's it. Okay, now there is another one, which is the circuit active load. So if I have like this, new 1, 2, 3, 2, 4, and I do it like this. So that means actively. What does it mean?
It should be the opposite of the first truth table.
Huh?
Truth table. It should be the opposite of the first truth
yes,
table.
So this table will be like this, exactly. So you're gonna be like this. Enable S1 is 0, D3, D2, D1, D0. 1, 2, 3, 4, 5. 0, 0, 0, 0, 1. I don't care and they're gonna be 0, 0, 1, 0, right?
Do we call this one active low or?
This is active low 2-4 decoder with
Thank you.
enable. Or, you know, to make it very, very, very efficient, we're gonna say that, you know, 2-4 decoder with active low enable. Because the rest are not active low, right? S0 and S1 are not active low. D0 to T3 are not active. When they will be active low, when they have this element, right? That means 0 will be the active one, it will not be the active, the reverse, you know what I mean? Is it clear to everybody? Joseph?
Yes, that's clear.
Wait,
could you do me a favor and make the circuit?
Which one? This one?
Oh yeah, this one, because I could apply that to the last one too. So I guess
it's up to you. I'm fine with that. You know, let's go for the circuit, right? So you know.
Thank you.
I don't know what's going on with my tablet, but it's been silly. You know? Hey, what the heck?
Are you charging it right now?
Yeah, it's.
Try to unplug the charger.
I don't know. I mean, maybe it's tired. Anyway, so it's gonna be S0, S1, enable, and I don't know why I made this one. Okay. Anyway, now we're gonna go into the solution of the 0, 0, right? And then, you know, I can just go like this. This is my line. This line, it will be ended with S0 complement, right? So that makes sense?
Yeah, that makes sense.
Then, yeah. And you will do the rest.
Awesome. Thank you, Professor.
Super. Any other questions?
We're good.
If there is no, oh, go ahead. Do you have a question? No? You don't have, right?
So just to make sure,
yes,
like active low, really it's just your technically you would have to put a pull down resistor, right?
No. Yeah, exactly. It's pull down. It's not pull up. Yes. They call it PMOS. The other one is called NMOS.
What's NMOS?
N, that means the electrons going between the source and drain in the channel. While PMOS holds, which is holding the positive charge going between the source and drain.
That makes sense, yeah. I know that.
Because what is the definition of the current? It's a bunch of electrons pushing each other between the source and drain. And the gates in the middle, you know, checking their ID. Whether that, you know, they have the permission to go or not. It's basically the same thing like the canal, right?
Yeah, so like PMOS would be like a emitter
like this.
And then goes to the collector.
And MOS like that. There's another one, it's called like this. That's called CMOS.
Oh, so they're connected.
They reverse each other. Do you know this circuit? It's actually building what? Building inverter.
Yeah, inverter, yeah.
There's a course, it's called VLSI. be covering this. But I can show you next time. Just somebody tell me, Professor, remind us. Then I remind you. Okay? I can make it next time. Can show you, even I can build the whole circuit using transistors. It's not a problem for me. Okay, look. So what is gonna be expected next time? So, you know, one of you guys, maybe Jamal or Malvin, you know, whatever, you know, or Christopher, you know, somebody remind me and say, you know, let's expand the decoder using small decoders. That makes sense? Then we'll move forward with the rest of the chapters. Hopefully soon we'll finish because, you know, as much as I can finish fast, as much as I can keep repeating. So if you have problems, I can just go back and forth, until, you know, everything will be clear. That makes sense?
Are we working on sequential logic next class? I'm sorry, what?
Yeah, you said, oh, you're working on what?
Oh, no. Are we working on sequential logic next lecture?
No. You know,
okay.
You mean after this chapter sequentially, yes. But, you know, this chapter still we have a lot.
Okay, cool.
I'm very slow, you know. I'm taking it very slow. Because the quality is more important, you know.
Awesome.
Very true.
Okay. If there is no other questions, I would like to thank you for the great work you are doing through this difficult time, you know. And I wish you a wonderful night. Stay safe and God bless you. Okay,
Thank you so much, Professor.
Thank you, Professor.
Thank you, Professor. God bless. Thank you.
Thank you, Professor. One quick thing after
yes.
in a second. I realized. Sorry for wasting time. But I was looking at the wrong feedback for 3-8. So my grade is correct.
Huh? What's it?
I was asked because I was confused earlier because I thought I did something wrong on 3-8 on 3B.
Yes.
But I was looking at the wrong feedback.
Yeah, dude.
Yeah, sorry about that.
So I'm gonna take the full point from you.
No.
Yes.
Oh wait, did you already add it?
Yes.
Oh, okay. I'm sorry about that.
But
yeah.
No. But you did a good job. You know, you're honest.
Yeah.
I know. I give you that.
I came back and I was looking at it. I was like, wait a second.
No. But you know, I really appreciate that you are really honest. You know, that's really good.
Oh, yeah. No worries. Thank you so much for the.
God bless you.
Professor.
Stay safe. Okay.
Yeah.
Thank you. Bye.
Professor.
Juan, stay. I need to talk to you.
Professor.
Yes.
I was just asking, like, just regarding my midterm. I feel like one of them was like I should have gotten the point, but I didn't on question 1B.
1 second. Grade school.
Sorry, Professor. I didn't want to bother you.
You're fine. You're fine. What's your name, sir?
Nicholas Serjani.
Nicholas Serjani, right?
Yes.
Which question, sir?
1B.
Let me see what is 1B.
You said like my implementation was incorrect.
Yeah, your implementation is incorrect, right? It's just an AND game. You shouldn't have NAND and NAND and NAND like this.
Because like I did the same thing in the previous quiz and you gave it to me correct, so I did the same thing. That's why.
No. This is optimized. I looked at the optimization.
Okay.
From now on, everything is optimization. Okay.
Got it. Thank you, Professor.
Okay. Yes. Brandon, do you have a question? No, he doesn't. Okay. So Juan, tell me what happened. So they give you the grant or not?
So So yes, I got accepted to the research.
Oh,
so I'll be working with you, Professor.
Let me